Hi everyone. By Haley's request, I'm doing homework number 41. This is pages 135 through 6, numbers 1 through 5, 8, 9, 12 through 14, from our rate of change day 1 assignment. Okay, so problem number 1 says write the volume V of a cube as a function of its side length. Okay, well that should be pretty straightforward. Volume as a function of the side length of a cube. Well, I remember this formula from middle school and from geometry, and if you don't, you should probably write this down on a page in your notebook called Formulas I Damn Well Better Remember for the AP exam. Okay, so, and notice we could even write this as V of S, because all we have is some S stuff over here. Part B. Part B says, find the instantaneous rate of change in volume with respect to side length. So we want dV ds. dV ds. Well, that just means taking the derivative of this relationship. When I take the derivative of both sides, I'm going to have 3s squared. So there's the instantaneous rate of change. Then it says evaluate the rate of change in V at s equals 1 and s equals 5. So for part C, we're looking for dV ds when s equals 1. So that'll be 3 times 1 squared, or 3. And we want to know dV ds when s equals 5. And so that's going to be 3 times 5 squared, or 75. I don't have any units in this problem, so I can't put any units on my answers, so stop worrying about that. And then finally, part D says if s is measured in inches, and v is measured in cubic inches, what would the units for dV ds be? Well, a change in volume is inches cubed, and a change in s is inches. Now, you're welcome to turn this into inches squared, but who the hell knows what that means? That's area. No, that's not what this is. This is a change in volume as the side length changes. So I wouldn't do that. It's not going to be wrong to write that. It's just going to be wrong to write that because it conveys false meaning. This is the meaning you should be striving for. A change in volume is inches cubed. A change in side length is inches. Okay? Okay. So when I look over here at 3 inches cubed for every 1 inch change in side length. That's how I understand that. I'm going to have 3 additional cubic inches of volume for every 1 inch change in side length when s equals 1. But when s equals 5, I'm going to have 75 cubic inches of volume for every 1 inch of side length change. Because these numbers are much bigger, the cube is already very big. If we go up by 1 more inch, we're going to be adding a lot more volume. Please don't write inches cubed over inch equals inches squared. That would just not be good. Okay, problem number 2. 2 says, write area of a circle as a function of circumference. Okay, well, I know the area of a circle is pi r squared, but they want area as a function of circumference. Do I know a relationship between radius and circumference? Sure do. I know that circumference is 2 pi r. Again, if you didn't know this formula, please write this formula down on your page called Formulas I Better Not Forget. Okay. Now, we want to get rid of r, and we want to introduce c. So solve the helping equation for the variable you want to get rid of, I want to get rid of radius. So I know c divided by 2 pi will equal radius. And so I'm going to replace this radius with c over 2 pi. Notice it's radius we got rid of. We didn't get rid of the squaring, so that squaring needs to be there. And yes, you need to apply the squaring here. So a of c is going to be pi times c squared over 2 squared is 4, pi squared. I can cancel a pi here with a pi here and get a of c equals c squared over 4 pi. Part B, that was part A. Part B says, find the instantaneous rate of change in area with respect to circumference. So they want dA dc. Well, if I take the derivative here, please don't use the quotient rule. Think about this as 1 over 4 pi, a constant, times c squared. The derivative of area with respect to circumference is simply going to be the derivative of circumference times that constant, or 1 over 4 pi times 2c. I can cancel 2's and get c over 2 pi. There's my dA dc. Part B. Part C says, why don't you evaluate the rate of change in A at c equals pi and c equals 6 pi. So dA dc at c equals pi will be pi over 2 pi, which is 1/2. And they want us to do dA dc when c equals 6 pi. And so we get 6 pi over 2 pi, or 3. There's part C. Part D asks us again to consider units. A is measured in square inches, C is measured in inches. We've got a change in area over a change in circumference. So for part D, I'm going to say I have inches squared over inches. Again, I'm not going to cancel and turn that into inches, because that don't mean anything to me. But here I can see 1/2 is 1 square inch for every 2 inches change in circumference. If I make the circumference 2 inches bigger, the area is going to increase by 1 square inch when c equals pi. But if c equals 6 pi, then 3 square inches of area for every 1 inch change in circumference. Okay? All right, next. 3. I hope by now you're starting to get the pace of these problems. The area of an equilateral triangle as a function of its side length s. Equilateral means all the sides are the same length. Side length is s. If I draw in the height here, that bisects this side length. So here we have 1/2 s, and here we have 1/2 s. I do see a right triangle here with the height 1/2 s and s. Okay? We're going to need this information because right now I know the area of a triangle is 1/2 base times height. Well, the base of our triangle is 1/2 s plus 1/2 s, or s, and the height is h. But I need area in terms of s's. So I'm going to have to get rid of this h and replace it with some s stuff. Can we get a helping equation? Well, back to this picture. Is there a relationship between s's and h's? Yes, there's a trig one, but no, I don't know the angle, so I don't want to go near the trig one. Instead, I want to use the Pythagorean theorem here. I want to say 1/2 s squared plus h squared should equal the hypotenuse s squared. So this will be 1/4 s squared plus h squared equals s squared. Or h squared equals, when I subtract 1/4 s squared from both sides, 3/4 s squared. But I don't want h squared, I want h. So go a little further, take the square root of each side, and what do we get? We get that h equals √3/2 times the side length. So I'm going to replace this h over here with √3/2s. So when I tidy this up, 1/2 times 1/2 is 1/4. There's a √3/4 then. S times s is s squared. A as a function of s. So this is the area of an equilateral triangle as a function of side length. If I know the side length of the equilateral triangle, I plug that side length in here, and I'll know the area of the triangle. Okay, so there's part A. What about part B? Find the instantaneous rate of change in area with respect to side length. Oh, well, they just want me to take the derivative of this. dA ds equals, bring down that 2, right, because it's just a constant, times s squared. Take the derivative of s squared. We'll bring down that 2. That 2 will cancel with a 2 in that 4. We'll have √3/2 times s. So there's dA ds. What about part C? Evaluate the rate of change in area at s equals 2 and s equals 10. Okay, I think I'm running out of space here. We finished with the helping equation, so let me use this space over here. C, we want to know dA ds when s equals 2. And so that's going to be √3/2 times 2, which is √3. And we want to know dA ds when s equals 10. And so that's going to be √3/2 times 10, or 5√3. Okay, part D, is it the units question again? If s is measured in inches and a is measured in square inches, what would be the units for a change in area over a change in side length? And again, that's inches squared per inch. For every 1 inch we add, we get this many square inches change in area. So when I see √3 as the answer up here, I know I'm getting √3 square inches for every 1 inch change in side length. Okay, number 4. Four says, a square of side length s is inscribed in a circle with radius r. Circle, square, radius. This is also a radius. Together, these two radius make a diagonal in the square. Okay? We know the side length of the square is s. What is it that they want us to do? They want us to write the area of the square as a function of radius. Area as a function of radius. Well, I know the area of the square is side squared. What we want in terms of radius. So we're going to have to find a way to get rid of radius, rid of side length, and get r in its place. So I go back to this right triangle again. And if you remember your 45, 45, 90 right triangle shortcuts, you're welcome to use those. Most people aren't comfortable with them at this point, so I'm going to go with Pythagorean theorem. And I'm going to say s squared plus s squared equals 2r squared. So 2s squared equals 4r squared. What is it that I want to do? I want to get rid of s squared. So I'm going to solve my helping equation for s squared, and I see that s squared equals 2r squared. So I replace this with 2r squared. Now I have area of the square as a function of the radius of the circle. There's part A. Part B. Are they asking me to find the instantaneous rate of change in A with respect to radius of the circle? Sure. They want to know dA dr. And that's going to be 4r. And then in part C, evaluate the rate of change in A at r equal to 1 and r equal to 8. Okay, so for part C, they want to know what dA dr is when r equals 1. And so we get 4 times 1, or 4. And they want to know what dA dr is when r equals 8. And so that's going to be 4 times 8, or 32. Part D, they're asking us about what units we would have for dA dr. Well, area is measured in square inches, radius is measured in inches. Okie doke, there's number 4. What's next? 5. Okay, 5 says, it's a table problem, and AP loves a table question. You should expect to see a table question as one of your 6 free response questions. Okay, so we've got, for number 5, this table, and the table features times in seconds and positions in feet. And we've got 0, 1/2, 1, 1.5, 2, 2.5, 3, 3.5, 4. I'm not going to draw those in yet. 12.5, 26, 36.5, 44, 48.5, 50, 48.5, 44, 36.5. Notice the object is going up, 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 and then starts going down, down, down. And it even appears as though there's symmetry here. So maybe it's a parabola. Okay, let's take a look at what we're asked for here. Part A, plot S versus T on a coordinate paper and sketch a smooth curve through the given points. All right, well, I'm not going to make too much of a fuss about this. So here's my 3, 50, and then I go back down from there. Okay? And they want a smooth continuous curve. So I've got some form of parabola where we have that symmetry that I mentioned before. Okay? Part B, assuming this is a smooth curve, represents the motion of the body. Estimate the velocity, v of 1, v of 3.5, 2.5, and v of 3.5. Okay, well, let's consider each of these. Remember, velocity is the rate of change in position with respect to time. So when I think about velocity at 1, I want to know the slope at 1. But I don't have a function here. And no, I'm not going to use a regression equation because it doesn't say build a regression equation. It in fact says that I'm supposed to estimate the velocity. So in order to estimate v of 1, I'm going to use average velocity. And I'm going to use the average velocity from 1/2 to 1. But wait a second, why don't I use from 1 to 1.5? In fact, the best thing I should do is average those two velocities. Average those two average velocities. So 36.5 minus 26 over 1 minus 1/2 plus 44 minus 36.5 over 1.5 minus 1. I want to average. I want to add them together and divide by 2. I want to average these two velocities. When I did this earlier today, I came up with 21 plus 15 over 2, or 18 feet per second. I'm going to repeat this process for v of 2.5, and when I do that, I'm going to have 50 minus 48.5 over 2.5 minus 2. That's going to be the average velocity from 2 to 2.5, and then I'm going to use from 2.5 to 3. 48.5 minus 50 over 3 minus 2.5. And remember, I want to add these two and divide by 2. Well, what I notice here is I end up with 3 minus 3, right? Because this is 1.5 over 1/2, which is 3, and this is negative 1.5 over 1/2, so that's minus 3. And so I end up with 0 feet per second. And that makes sense because we're talking about our maximum here. And what do we think about the slope at that maximum? We think we have a 0 slope, 0 velocity at 2.5. Okay? And then we'll repeat the process for 3.5. We really should be comfortable with this now. Part C, V of 3.5. And so I'm going to have 44.85 minus, 44 minus 48.5 over 3.5 minus 3 plus 36.5 minus 44 over 4 minus 3.5. So I'm finding the velocity here, the average velocity here. I'm finding the average velocity here. I'm adding those two average velocities together and dividing by 2. When I did this, I got negative 9 plus negative 15 over 2, which is negative 12 feet per second. We're going down. The slope here is on average negative 12 feet per second. Okay, that was number 5. What's next? 8? 8. Okay. 8 says draining a tank. Draining a tank is a very common AP thing. Q of T, quantity as a function of time, 230 minus T squared. How fast is the water running out at the end of 10 minutes? How fast is the water running out at t equal to 10 minutes? Well, how fast? That's the rate of change in the amount of water. So what I'm looking for is q prime of 10, which means I need to take the derivative here, which means I need to do something with this. We know that q equals 230 minus t times 30 minus t. Well, that's going to be 900 minus 60t plus t squared. And when I distribute that 200, 18 with 4 zeros, minus 12 with 3 zeros, plus 200t squared. That's q. So q prime, derivative of this is 0. The derivative of this is negative 12,000. Be careful about that negative sign. And the derivative over here is 400t. Okay, so if I want q prime of 10, then I want to plug a 10 in. And I get negative 8,000. What are the units? Well, they told us that quantity is measured in gallons and t is measured in minutes. So this is gallons per minute. 8,000 gallons per minute. This is draining very fast. Okay, what's next? What is the average rate at which water flows out during the first 10 minutes? Well, that's not Q prime of 10. That's instantaneous rate of change. We're looking for average rate of change in Q across those 10 minutes. We're looking for Q of 10 minus Q of 0 over 10 minus 0. Okay, so I found Q of 10 to be 80,000. And I found Q of 0 to be 180,000 over 10 minutes. So I get negative 100,000 over 10, or negative 10,000 gallons per minute. On average, the tank is leaking 10,000 gallons per minute every minute for the first 10 minutes. At time equal to 10, the tank is draining exactly 8,000 gallons per minute. Okay, there's number 8, a typical AP question. Number 9. Nine comes with a picture, and the picture is a graph of V equals F of T. Here's that picture, so you can see it too. All right, so let's talk about what's happening here. This is a velocity of a particle moving on a coordinate line. When does the particle move forward? When does the particle move backward? Okay, so I know, I think I'm just going to graph this, because I'm going to need 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm going to need 2, 3, and then up to 5, and 6, and 7, and flat line. Okay. So, we know that when V is greater than 0, the object is moving forward. And we know when V is less than 0, the object moves back. So, if this is a graph of V, I say the object is moving forward, and that's part A. When does the object move forward? When velocity is greater than 0. So on 0 to 1, union, 5 to 7. When is the object moving backwards? Whenever velocity is negative, so from 1 to 5. Okay. B. When is the particle speeding up? Well, remember, speed is the absolute value of velocity. So if I want the absolute value of the graph, I have to take all this negative stuff and flip so here's my velocity, here's my speed graph now. Okay, so then they ask, when is it speeding up? That means, when is the speed graph increasing? Well, speed is increasing from here to here. So, from 1 to 2. I also see that the speed graph is going up, increasing from 5 to 6. And when is this thing slowing down? I imagine is the next question. Yes. So, slowing down, we're looking for the speed graph to be decreasing. And we see that happening over here from 0 to 1. And we see it over here from 3 to 5. And we see it over here from 6 to 7. Okay, so all that was part A. Part B. When is the particle's acceleration positive, negative, or zero? Okay, so what's acceleration? Acceleration is the rate of change in velocity with respect to time, also known as acceleration equals the slopes on velocity graph. So if I'm asked when is velocity positive, if I'm asked when acceleration is positive, that's when the slopes of v are positive. Well, here's the v graph. When are the slopes on v, not speed, when are the slopes on v positive? Negative slopes, zero slope. Ooh, here I have a positive slope from 3 to 6. And when is acceleration negative? Acceleration is negative when the slopes of velocity are negative. Well, I see the slopes of velocity are negative here from time equal to 0 to time equal to 2. And I see some negative velocity here, negative acceleration here, because the slopes of velocity are negative here from 6 to 7. Okay? And they also asked us, by the way, when is acceleration 0? A equals 0. And that's when the slope of velocity equals 0. So from 2 to 3 and from 7 to 9. Okay, that's B. What about C? When does the particle move at its greatest speed? All right, back to the speed graph again. Greatest speed. Well, remember with our speed graph that we reflected this up. And greatest speed looks like the highest y value on the speed graph. So I would say C, greatest speed on 2 to 3. Okay? I saw this, you can look at the graph yourself. I saw this amount to be more than this amount. But look, if you thought this amount was bigger than this, all right, you claim t equals 0 is when speed is greatest. But I thought this distance was greater than this distance. And if they're the same, then you say time equal to 0 and between 2 and 3. Okay. You could always get out a ruler and measure it. I'm just trying to get done with this because this is my third video tonight. Thanks, Haley. Hope you watched this. All right, when does the particle stand still for more than an instant? Stand still means V means not moving. Means V equals 0. V equals 0. Up, but that's just at an instant. V equals 0. Up, that's just at an instant. Here, though, from 7 to 9, velocity remains 0. Okay? So there's number 9. All right, last 3 problems. Let's see what we got. 12 through 14. Okay. 12. Hello, 12. There we go. All right, 12 has lots of parts. Ooh, yay. Just like an AP question. Wouldn't be an AP question if it didn't have D or E parts to it. 12. Now 12 is kind of weird because it comes with a table, and we're going to see lots of tables this year, but our input is furlongs, that's a distance, and our output is time. Normally time is our input, and distance is our output, but not in this function. In this function, furlongs is the input and time is the output, okay? So we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 10 furlong race, and the amount of time, 20 seconds to cover the first furlong. We get to the second furlong at time equal to 33, the third one at 46, then we get 59, 73, 86, 100, 112, 124, and at the 10th furlong, the end of the race, 135 seconds. Okay, so part A, how long does it take the horse to finish the race? The race is 10 furlongs long, so it takes the horse 135 seconds. A little over 2 minutes to run this race. Good. A, 135 seconds. Hey, don't forget to write sentences for these. B, what is the average speed of the horse over the first 5 furlongs? Okay, speed is a change in furlongs over a change in time. So when I think about speed over the average speed over the first 5 furlongs, I've got 5 minus 0 over 73 minus 0. So 5 furlongs every 73 seconds. That's my average speed. C, what is the approximate speed of the horse as it passes the 3 furlong marker? So here in part C, they're asking me for instantaneous rate of change at furlong equals 3. So I'm going to do that thing that I did a few minutes ago where I find the average rate of change here and the average rate of change here, and I average those two average rates of change. Okay? So the change here is 3 minus 2 over 46 minus 33. And the change here is 4 minus 3 over 59 minus 46. And we want to average those two numbers. So that's going to be 1 over 13 plus 1 over this minus this is 13 over 2. So I've got 2 over 13 divided by 2, which is 1 over 13, 1 furlong every 13 seconds. That's pretty fast. 220 yards in a furlong, 220 yards. So think about that as a little more than 2 football fields every 13 seconds. Go ahead, football players. That's a lot of running. 2 football fields every 13 seconds at the 3rd furlong. This horse is moving. Okay, D. During which portion of the race is the horse running fastest? Okay, so in order for the horse to be running fastest, we want this number here on the bottom to be smallest. These are all going up by 1 second increments. Okay, so if I find the slope from 9 to 10, that's 1 over 11. And if I find the slope from 8 to 9, that's 1 over 12. And here I have 1 over 12. And here I have 1 over 14. And here I have 1 over 13. And here I have 1 over 14. And here I have 1 over 13. And 1 over 13. And 1 over 13. And 1 over 20. Slow start, took 20 seconds to get up speed and travel that first furlong. When was the fastest furlong? When we covered 1 furlong in only 11 seconds. Again, 11 seconds to run more than 2 football fields. Really fast. This horse is driving hard to the finish line. Okay, so our question here for part D was, during which portion of the race is the horse running fastest? So D, during the last furlong. Now, I need to compute all of these to see that 1 over 11 is in fact the shortest amount of time to cover 1 furlong. Okay, and then finally part E, during which portion of the race is the horse accelerating fastest? Accelerating fastest. That's the greatest change in these slopes. And where's that greatest change? Here, between the first and second furlong. It takes 20 seconds to run the first furlong and only 13 seconds to run the second furlong. This horse is making a dramatic increase in, it's accelerating. That's what the horse is doing. The horse is accelerating greatest. Here, acceleration is 0, acceleration is 0. I'm looking at the changes in these numbers. This is actually going slower. The horse is slowing down. Then the horse sped up again. Then the horse is slowing down. Decelerating, accelerating, decelerating. Ooh, big burst of speed, accelerating, constant, and then accelerating again. But this is only a change of 1 unit. Here I have a change of 7 units. So my answer to E is between the first and second furlong. The horse is accelerating fastest. Okay? Though, I guess, well, wait a second. What about during the first furlong? It goes from 0 to 20. That's an increase of 20. So, yeah, I changed my mind. I say during the first furlong. Okay, so there's 12. 13. 13 says we've got a lunar projectile. S equals 24t minus 0.8t squared. And this is a rock thrown vertically from the surface of the moon. Reaches a height given by S, so this is height in meters, time t in seconds. Part A, find the rock's velocity and acceleration as functions of time. Okay, so v of t, we know, is s prime of t. So if we take the derivative here, we get 24 minus, don't forget the power rule, 1.6t. And a of t is v prime of t, or s double prime of t. So I want to take the derivative here, and I get negative 1.6. What would the units be here? Well, the units here are meters per second, and the units here are meters per second per second. This is the force of gravity on the moon. Ours on planet Earth is 9.5-ish meters per second. So there's a lot less gravity on the moon than there is here. Okay, part B. How long did it take the rock to reach its highest point? Well, as we saw earlier in this conversation, the highest point, the highest position, will have a horizontal tangent, and therefore velocity will be equal to 0. So I'm going to find when v equals 0. 24 minus 1.6t equals 0. 24 equals 1.6t. 24 divided by 1.6 equals t. What is 24 divided by 1.6? It is 15 seconds. So it takes 15 seconds to reach the highest point. Okay, that is B. How high did the rock go? Well, we want to know position. So we want S of 15. We want to know what's this height when t equals 15. So we'll plug that 15 back into the height equation. 24 times 15 minus 0.8 times 15 squared. And when I compute this, I end up with 180 meters. 180 meters up. Wow, that's pretty far up. Okay, part D says, when did the rock reach half its maximum height? Okay, so the maximum height was 180. Half of the maximum height is going to be 90. And we're wondering when position 24t minus 0.8t squared equals 90. Well, I'm not going to be solving this by hand, and you're welcome to use the quadratic formula. But I graphed this in y1, I graphed this in y2, and I found out that this will occur, these will be equal to each other at time equal to 4.393 seconds and time equal to 25.6 seconds. Think about what it is we've got here. We've got 90 meters, once going up at 4.393, once coming back down at 25.6 seconds. Can you imagine throwing a ball and it taking 30 seconds to hit the ground? I mean, that's a lot of air time. Okay, and then part E says, how long is the rock aloft? Well, I want to know when the rock hits the ground, which means I want to know when position equals 0. For part E, I want to set position equal to 0. Well, I did this by hand. I factored out a t and had 24 minus 0.8t equal to 0. T equal to 0, sure, it's on the ground. Then it goes up, and there's this second time when 24 equals 0.8t, or t equals 30 seconds. It takes 30 seconds for this thing to hit the ground. Okay, 14. Free fall. Free fall problem, pretty fast. It's free fall on Mars and free fall on Jupiter. Mars equation, oh, sorry, not Mars, but the, oh wait, yes, it is Mars. Mars position equation is given by S equals 1.86 t squared. And on Jupiter, S position is given by 11.44 t squared. Okay, how long will it take a rock falling from rest to reach a velocity of 16.6 meters per second? Hey, meters per second, that's a velocity. So what I need to be looking at is not these position equations, I need velocity equations. So velocity is s prime, so I need to take the derivative of this, and when I take the derivative of this, I get 3.72t. And I want to know when 3.72t is equal to 16.6. I divide both sides by 3.72, and I get t equals 4.462 seconds. Over here, again, I want velocity, that's s prime, which is going to be 22.88t, and I want to know when velocity equals 16.6. So I want to solve this equation for time. I get 16.6 divided by 22.88, which is approximately 0.726 seconds. Wow, it takes less than a second to be going 16.6 meters per second. Here it took almost 5 seconds to get to that speed. Things are hopping on Jupiter. Okay, it's funny because I would have expected Jupiter to be a lower gravity planet because it's got such a larger radius. But I guess I stand corrected. All right, well, that's the homework, Haley. I hope it helps, and I look forward to answering your questions soon. Bye, everyone.